Ready?
Good morning, everybody. Welcome of the offline mode of AICT Hotel sponsored faculty development program titled Innovative Micro and Nanotechnologies and Fundamental Applications by the Department of Mechanical Engineering. At the outset, I'd like to invite all the participants as well as dignitaries present on the dais. Professor Deepak Ghosh, Chairman, Industry Institute Partnership Cell, University of Technology. Professor Tarun Kali Jana, Dean of Engineering, Haldia Institute of Technology. The Head of the Department, Mechanical Engineering, and the coordinator of this faculty development program, Professor Gautam Kumar Ghosh. And last but not the least, today's eminent speaker, Dr. Sudeep Ghosh, Department of Mechanical Engineering, IIST. So at the outset, I'd like to request Professor Jana to felicitate Dr. Ghosh with bouquet. I'd like to request Professor Deepak Ghosh to welcome sir with the So we are all set to begin the second day and another exciting lecture of this faculty development program. So let us begin with a brief bio sketch of the today's eminent speaker. Dr. Sudeep Ghosh is an associate professor in the Department of Mechanical Engineering, IIST Shibpur, and presently serving as the head of the department. A 1991 graduate in Mechanical Engineering from Jalpaiguri Government Engineering College, North Bengal University, he holds master's degree from Bengal Engineering College, which was under Calcutta University, and PhD from Jadavpur University. In his professional career spanning over 3 decades, he both served in the industry as well as academia. Initially, he worked as an engineer in ABL Private Limited, Durgapur, which was later renamed as Alstom Power Limited, for over 7 years, and thereafter joined the College of Engineering and Management, Kolaghat, as lecturer in 1999. Later in 2002, he moved to the erstwhile Bengal Engineering College, presently which is known as IIST Shibpur. So he also served as a guest scientist in Paul Scherrer Institute, or PSI, in Switzerland. Dr. Ghosh's area of interest is area of research includes clean coal technology, greenhouse technology, renewable energy technologies like fuel cell and biomass gasification. At IIST, he played an instrumental role in creating biomass gasification test facility and the thermal simulation and computation laboratory. Together with his scholars and students, he has authored more than 60 research papers in several reputed international journals and conference proceedings. He has also authored a few book chapters of his research works. With this brief bio sketch, I'd like to invite Dr. Ghosh for his lecture.
Good morning. Thank you for the nice introduction. Respected Chairman, IIPC, respected Dean, respected Head of the Department, Professor Ghosh. Yes, it's indeed nice to be back here after a long time. Perhaps it's 7-8 years back that I came to this department for some other similar occasion. Although perhaps a couple of years back, I gave one talk in some other program, but that was online mode. So physically speaking, this is, I think, after a long time, not less than 7-8 years I have been back here. Well, the program is AICTE sponsored FTV program. So I believe members in audience will have representatives from teaching communities from this institute as well as from outside. Many might be mechanical, some might be outside mechanical. The topic is, this talk will not really be about nanotechnology, but yes, the application of fundamentals. If I may say, the fundamentals of thermodynamics, thermodynamic postulates, how do we use analytical tools of thermodynamics into system analysis. Yes, my area of research is primarily energy oriented, so energy technologies, energy system modeling, experimentation. Now focus is more on renewable energy, although in the initial years of my career I used to work in coal gasifications. Even you can say my work for PhD was also in coal gasification or clean coal technology. But then gradually the focus shifted to renewable energy. So many of the applications that even what I may discuss here also, that would include instances of renewable energy technology. Well, with that, let me start. But I have to. So I believe without this audio system, yes, I can operate. Okay, so we'll operate here. Well, thank you. So yes, this is the perspective. For the topic. So most energy conversion systems we used to study in terms of the basics of thermodynamics, the fundamental principles. The primary one being what we derive from the first one, right? For example, efficiency is the term that we often use for effectiveness of any energy system or energy equality. But how can we apply it to complex systems, or compound systems? Right? How it works? What more opportunities are there? So primarily, these things are changing. The criteria is changing. So no more you can say. Only we can talk about efficiency. There are a lot more things. If we move on to the next slide, you'll see what are our questions when we try to design or think of a new system. The first thing we look for, is it coming from renewable sources? What kind of resources we are talking about? How effective is the technology? Is the technology matured? How developed it is? Can it yield multiple products simultaneously? Now, when I say product, that means these are the primary output of the system. But apart from the primary outputs or the important or desired outputs, can we have some other byproducts which could be recovered, could be used, could be utilized in some other ways? What about the losses? What about the wastes? Are they harmful? Are they benign? Can they be made useful? These days we are concerned about the environment. To be precise, the primary focus is on carbon emission. So we try to find out what is the carbon footprint. This is particularly important for conversion systems, not sourced from renewable energy. So, apart from carbon emission, what other environmental implications might be there? It's not only carbon emission, as you can conceive. A power plant, let's say it's traditional power plant working on coal-based power through steam generation. So steam-based cycle, steam-based power generation system. It doesn't only emit carbon dioxide. It also gives out a lot of things. For example, think about the heat rejection to the environment, to the cooling water. Think of the ash disposal. Very big problem. How do you handle that? Today's Indian pool comes with more than 30% of ash content, 30-35%. That means 1/3 is going to be ashes. Right? So if a power station consumes 3,000 ton a day, it will be producing 1,000 ton a day of ash. So how do you dispose of that? So these are the questions that keep coming. Then comes the question of economy. Cost of electricity, the common term that we know. So how is the economy? Is the system going to be economically viable? Considering the products that we are thinking about, what about the payback period? How long will it take to get my money back that I have invested today? Is there policy supports available from the local government, national government? Is there policy supports available from international community? So these are the queries that we tend to ask, and it's because of all these factors we tend to deviate from the basic principle or basic criteria of judgment. So that's why obviously if you are designing something only looking at efficiency, you cannot really address all these questions. So that's why I say we tend to deviate from this very basic principle or very basic mode of assessing an energy technology. Yes, please, next one. Now, this is what we teach in undergraduate courses. We teach when you get work out of a system. I mean, the example only shows a heat engine application. Right? So you get work out of some source, you send out something to see, and you evaluate its efficiency based on what output you get over what input you have. So the base one, I mean, you simply say the thermal efficiency is the work output by the heating. Now, when the application is reversed, we are not really talking of work production or power production. We are talking of cooling, or maybe we are talking of heating. Then we do not use the term efficiency, isn't it? We use something. If we call it efficiency, then that is going to be more than one in most cases. So we devise a term called coefficient of performance, implying what we are desiring, and to get that what we are giving as input. So if your desired effect is the cooling effect, you put that cooling effect divided by what input means what input we are giving, right? So that's what is called COP. Now then that COP, that will differ if you think in terms of refrigeration or if you think in terms of heat pump. When you are interested in heat pump, you are concerned with the heat that you are rejecting at the higher temperature, isn't it? We do that as teachers. The students also know that because this is the basics that we teach in first or second year undergraduate students. And there again, COP of heat pump is not really same as the COP of refrigeration, right? COP of heat pump being more than COP of refrigeration. We know by what amount? Any direct relation you can establish between COP of heat pump and COP of refrigeration?
COP of HP is equal to COP of
yes, so
plus 1.
Yes, one is going to be larger than the other by 1. Well, now, okay, for the time being, let's forget about COP, let us forget about heat pump system. Think of in one case the product is only work. In the second case, apart from work, we are also thinking of something else, some utility heat. So in a similar mode, we are trying to have a combination of system because the focus is I mean, as you might have noted, the topic more than one. Most often by cogeneration, CH. Very basic cogeneration is combined heat and power. But cogeneration, when you expand it, that includes, for example, if you are having a system that produces power as well as cooling, that can also be cogeneration. So that will be cogeneration of power and cooling, right? Or cogeneration of power and refrigeration. So that is also cogeneration. So very basic cogeneration is the generation of work as well as utility. Now see, when we are talking about generation of work, we put efficiency. When you add something to that, if when you are adding this utility to that work, you can still use efficiency. But is the relevance remaining same? Is the implication remaining same? For example, if I ask you what would be for the first thing, you know what is the limit. The limit has put by way of the Carnot efficiency, because we know if you are using a heat engine system, you are, so the efficiency of the system is dictated by the Carnot efficiency. Carnot efficiency gives you the maximum of that. What about the second one? The moment you go for work, heat production apart from work, you find, is it limited by that Carnot efficiency? What is your guess? Can it be more than Carnot? Isn't it? Think of the very basic system, or for example, look at the expression of the second one: work plus heat divided by the heat. If I try to go for less of work, more of heat, are you going to gain? Yes, you are going to gain. In fact, it will be the maximum when you will have no work but almost, everything did. So that is going to give you 100% efficient system. It's only transfer from higher temperature to low temperature. So without going via any work production system. Right? So this work production system puts something. So in a way, this tells us that you cannot really compare the two things in a similar fashion. Right? So heat and work cannot really be considered in the same bracket. In fact, that's how we talked about second law. That's how we talked about. Perhaps you could guess we are trying to move towards something away from first law or something towards exergy. Yes, we will be, because these are the bases that forced us to think in a different manner than the one that we have been considering as a very basic principle. Okay, now come to this one. So, apart from efficiency, is there anything else that we could use to judge the performance of this combined system? Yes, there are ways of doing that. This is one way of doing. For example, if we were not having this combined system, what we have to do? Let's say we require both work as well as heat. So what options do you have? You have one option to get to separate plants. One will give you work, the other will give you heat. So I am showing two different plants, one giving you utility heat, the other giving you work. So when you are talking about this work, you are basically talking about the efficiency of the engine system or heat engine system. When you are talking about only the utility heat, you simply have the efficiency of your heat exchanger. For example, boiler, you need utility heat. So the easiest thing is to generate some steam and supply to your application. So that's how most often we consider utility heat. So that here efficiency will simply be the efficiency of the boiler. Right? So by combining, are you gaining something? So not only efficiency, you could look at what gain are you able to achieve because of this combination. When they are separate, they are consuming certain amounts of fuel. By combination, am I economizing on the fuel front? Right? How much are you saving? If you are saving, then you could say yes, by combination I could save something on the fuel energy. So that's why this is a relevant parameter for judging performance of such cogeneration system. This term might be known to people who are in research, but might be new to people who are not really working in CHP area. So we call it a FESR, fuel energy saving ratio. Right? So you put the saving in the numerator and you put the fuel energy when you were consuming it separately. So that was your original consumption. So saving over the original consumption, that gives you fuel energy saving ratio. Very simple. Problem is with this refrigeration or heat pump system. The first thing is, as I mentioned, the COP of heat pump and COP of refrigeration is not really same. Even though it's basically the same thing. Am I changing the heat amount? It's the same heat that is flowing from low temperature reservoir to high temperature reservoir. But we are defining it separately. I mean, that's how we are trained to do. That's how we have been taught to express. So we express the same thing. When you say it's our desired product is heat pump, we say COP of heat pump. When you say desired product is cooling, we say COP of refrigeration. And COP of heat pump, as you have said, it's more than COP of refrigeration by 1. Now see, this is indeed tricky. So I try to put the COP, Carnot COP. Now see, here I am talking about the Carnot COP operating between two temperature limits. The funny thing to note is that the change in COP values. Right? See, larger COP means, see, if you recall the COP, or you see the top expression, COP means the desired product over the required unit. So naturally you would like it to be more, because the higher COP would imply that you are giving less to get more. Now see, what actually is happening? Think in terms of the ideal parameters or Carnot values. No, so if your lower temperature is shifting, let's say I consider lower temperature from -10. So okay, environment is at 25. So it's -10. The COP was 7.51. When I consider it 0 degree, the COP increases. When I consider my lower temperature still higher, 5 degrees, the COP increases more. So going by the COP, it is giving me a feel that my machine is better and better. But actually, is the machine is better? Is it doing anything good? It's because its refrigerating point is shifting. So in a way, the first machine was maintaining -10 degree, the third machine will be maintaining 5 degree. But that is how we are trained. So we show higher COP for a machine which maintains higher temperature at evaporator, not lower temperature. But that was about VCR. Now then VCR and VAR, VCR and VAR are not really the same. Because when you talk about VCR, see, it's the same evaporation, same evaporator we are using. But in VCR, our input was what? Right? What is VAR? What is the full form of VAR? Vapor absorption. So what is my input there? So I get heat input. The heat input, I haven't shown that the heat input goes into the generator. Right? So basically, there is a secondary circuit that moves between absorber and generator. So in the generator, when you supply heat, the refrigerant gets evolved from that mixer, goes to the cycle, right? And the reagent comes back. So that's how this absorber generator circuit works, and the driving force is heat. So what I achieved? I achieved cooling system without any physical work input. Even though it's not really true, because you will need some work input through the solution pump, because there is, you see this pump. So the pump takes a little bit of work, but primarily it is heat driven. Now if I try to put COP, the COP for the first one VCR system is simply put, the denominator will be simply compressor water. For the second one, the denominator is different. So basically this pump work is negligible, you can see. So for the second one, the COP is having a term at the denominator which is far different compared to the term that you have in the first one. So there you had a term work, in the second one you have the term heat. So naturally their values cannot really be same. Now which one do you think will give you higher COP? The VCR one, because VCR one the denominator is what? Right? So that is going to be less compared to the heat. So COP of VCR system. So a VR system cannot compete with a VCR system. That's what I wanted to say. Right? So VR system, how better you feel that VR system is going to be, it's going to be worse performer compared to the VCR system when you try to compare COP, right? Because in the COP of this commercial systems, cooling systems, these are having values 5, 6, 7, 8, 9. But for VR system, hardly you can get a value approaching 1. So in most VR systems will have values 0.5, 0.6, 0.3, 0.4. As you will see, we have results here also. There also you will see for VR system actually 0.3, 0.4 is quite enough. But for VCR, we can start from 3, 4, 5. So there are things to be pondered upon. For VR system, the ideal system, the ideal COP you could put in this form, right? So the ideal COP is basically comes from the product of COP, Carnot COP multiplied by the Carnot efficiency of the generator absorber limits, right? So that is how. So the theoretical value has been calculated. See the theoretical value. The theoretical value is 1.35, and that is why in reality hardly can go get a value approaching 1. Always you will get a value less than 1. This is for this. Okay, looking at the expression once again. Yes, you could fine tune in the sense. In the first VCR system, my input was work, but if you are means it's a compressor work input. Now compressor work input, it's not only the work that you are giving into the compressor, you are basically giving electricity, right? So if you take that into consideration, then that term is going to be greater based on what efficiency you are using, right? Now think of the second term. Now that's VR system. One term is heat, the other term is water. Means there are ways of equalizing. You could say, I will consider work and heat together. Either I will bring all of them to work parameter, or I will bring all of them to heat parameter. So that way, for the first case, instead of work, you could consider equivalent heat, because that work is coming from electricity generation. Somewhere you are generating that work, then you are consuming here. So it might have some other efficiency somewhere else. So divide by the efficiency, you will get the heat input. So that way you could attempt of equalizing the denominators on both sides. Then you could compare. So is there a ready-made way of going into that or doing that? So these are the questions. Okay, but now the problem gets further complicated. Now if I say I will try to develop a system which will give me both work and now cooling also, right? So the first difficulty I face, what is the conventional performance parameter I should use? Nobody taught us, right? In engineering studies, hardly are you taught that you have to consider such a system and then you have to find efficiency. If I ask you to find efficiency, you will be at loss. You will be at loss even if I ask you to find COP. You do not have any straightforward way of either finding efficiency or the COP. Right? If you try to say, okay, let's say I will go by efficiency. So what parameters should you consider in efficiency? What it is showing? Is showing in the first heat engine was giving me some watt. Then I am using some watt as watt, and the rest of the work I am sending it to a VCR plant to produce cooling effect. Am I doing anything wrong? No. What I am doing, I am simply splitting the watt into two. One part I am consuming as watt, the other part I am sending to another cooling plant. And I am trying to judge efficiency. Now I am at loss. What should be my efficiency? Should I consider watt? Or should I consider the heat that I am transferring by utilizing that heat, that watt? So these are the complexities, or these are the questions, these are the queries that come. I mean, you can say these are wild thoughts. In a way, these are very basic, but these are wild thoughts. Right? I thought of sharing such wild thoughts with you. Who knows, maybe you would take interest in finding newer routes of assessing such complex systems, because the systems are getting complex, more and more complex day by day. Because need is there. Today we want to make system which will be double efficient. We want to make system which will be the efficiency term is may not be appropriate, but we want to make system which will be more effective, which can perform a lot of tasks simultaneously, giving work, producing code, giving heat, maybe giving something else. Right? So the things are needs are changing constantly. Okay, now think of this. What could take the form of efficiency if we split it? Let's say the first engine, let's say the engine is 40% efficient, right? So 40% efficient means the total work is basically 40% of the heat input. Get my point? The total work is 40% of the heat input. Now split it into 50-50. So I would say that W1 and W2 each will be taking 20% of the heat input. So one watt remains at watt, the second watt, which is W2, which is 20% of the heat that you send to the cooling plant, VCR plant, and let's say I have got a moderate VCR of COP value of 5. Yes, I consider 5. Now see the effect. If I consider COP value of 5, then the overall efficiency, if I want to put it that way, if I want to assess it that way, that efficiency is going to be more than 1. Right? Now, if you say whatever what I am producing, entirely I will send it to the VCR system, you will find efficiency is going to be down. So what is it? Is it a right way of dealing with these things? So these are the queries that keep coming when you try to work with such systems. In fact, it is because of that we try to look for newer avenues. In fact, the avenues were there, but we still needed to reorient ourselves to those things, as we will discuss now. So I got it that way. So that means it is not really good. Even though by coupling a engine to a refrigerator I am going to get 100% efficiency, but that for obvious reason that is not going to give me a very good solution. Okay, the earlier example was talking about splitting of work. Now splitting of work was necessary if we are requiring VCR system. Now if I use VR system, I don't need work, because we already have seen VR system works on heat, VCR system works on working. So okay, so I want to use VCR, rather let me integrate a VAR. Why did we consider this? Because this is a usual scenario. in many of our water producing applications, we get waste heat. You run an engine, let's say you run a diesel generator, it will be giving you waste heat. You run a steam power plant, that will give you plenty of heat rejection. Means everywhere, and in fact that is dictated by second law. Second law says you have to reject heat to produce work. You cannot convert 100%, isn't it? So if you cannot convert 100%, there is always going to be some rejects. So if there is going to be rejects, why not use that rejects to run a VR system? That again will give me some cooling. So that's what I attempted doing. And then I tried to use the same assessment technique, and I find this system is showing me efficiency of 70%. Good enough. Now tell me, if I produce less work and produce more heat, is it going to be more efficient? Ponder upon that. That's another interesting thing. But the thing is, this is better way of utilizing that, because I am trying to retain my work. I am not splitting my work. I am retaining my work, and the heat that was otherwise going to be wasted, I am utilizing that waste heat in running a VR system and then trying to increase my effectiveness of the system. So here comes the idea of exergy, very handy. Because exergy, by definition, exergy is basically the idea of work that would derive from some heat energy available. When we talk about the thermal energy, right? In very basic sense. For chemical, exergy will be something, but for heat, because the examples that we have mentioned all are basically based on heat or heat pump. So there, the work convertibility is what is exergy is all about. When you talk about exergy, we think in terms of the work producibility of the resource. That's all. Okay. There are different aspects of it. You can call it, you have physical exergy, which will be depending on the pressure temperature parameters along with the environment. If you think of chemical exergy, it will be depending on its chemical constituents, its composition. If you think of other forms of energy, they will also be constructing energy. For example, kinetic energy, potential energy, they are, but in most cases, these are the things which are usually neglected because of their negligible character, negligible proportion with respect to the other parameters of importance, right? So in most cases, these are neglected. So we are left with physical exergy or thermophysical exergy and chemical exergy mostly. Now, considering that exergy concept, now try to see what would be the exergetic COP of that VCR system. At most, you can approach the value of 1. Right? So that limits that criteria, limits that scale. Right? But note it for heat available at low temperature, the exergy expression is something else, right? Because the environment is a higher temperature compared to your evaporator temperature, so the expression of exergy is a little bit twisted, you can say. But many you are knowing that. So going by that, for VR system in the denominator we had that heat part. In the numerator also we had the heat part. So you replace the heat parts by the corresponding exergy expression for them, so you get the exergetic COP. Now it might be interesting to compare VAR and VCR by their COP, exergetic COP. Okay, so we took some, we are considering ideal cycles, but we considered the refrigerant fluids, different refrigerant fluids and their corresponding properties. We kept same, the load, cooling load we considered same, and we found that exergetic COP, look at the exergetic COP values, right? While the two systems were far apart in terms of their COP, now in terms of their exergetic COP, they are closer, right? So now you can say we are successful in getting them on a level playing field, isn't it? So now you can say I will compare this year and here on same platform, right? So that is the beauty of these things. In both cases, environmental considered 25 GT, and the other terms are not mentioned in here. But in both cases, look at the exergit extraction also. Exergit extraction means in most processes we will have destruction of exergit when it flows. We have considered the real fluids, means that two different fluids. So the extractions will also be there. That is also matching along with the exergetics. Well, so having done this groundwork, now we could try to apply this knowledge or apply this technique to some systems. Okay. So the case in hand is a gasification based system, biomass based system. Just to give you some intro about biomass based system, the most popular system from the biomass side is a biomass based gas engine system, right? The system is having one gasifier. The extreme left, on extreme left you have the gasifier which gasifies the gas. On the extreme right you have the engine which consumes the gas, like your gas engine. All the things in between are primarily meant for cleaning the gas, because the gasifier is not a good fellow, right? It gives out bad gas, very dirty gas. I mean, we have pictures also, you will see what kind of dirty will be. So you need to clean that gas, because that bad gas will not be accepted by the engine. So you need all these things cleaning, right? At the end you will get engine to run on that gas, but the entire system will be giving you not a good efficiency, but will be around, let's say, 18%, 20%, 22%. Right? Hardly you can go beyond that, because your gasifier might be limited to the efficiency of 70%, 75%. Your engine is restricted to efficiency of, let's say, 30%. So together they cannot really give you efficiency more than 21%, 25%. So that's how these are restricted. So that's why the system cannot really be much efficient. It can hardly give you efficiency of 25%. If it gives, that is going to be a good one. Yes, this is the facility we have at IIST. The top left is showing the main reactor. The red one is the gasifier. So after the gasifier, whatever you find, all are basically meant for the cleaning, right? We have this spray one for cooling. Then you have this filters, different kinds of. We have 3 bed filters. The bed filters in the second one you can see the bed filters behind the console panel. The second one is showing also the loads. I mean, it was just very trivial system. We just connected a number of filters. This was a 12 kilowatt system. So what we did, we got 12 1 kilowatt heaters. So we put them one by one to increase load. Yes, it was running perfectly. So it can run. The gas would be clean, but to clean the gas, a lot of tasks needed to be removed. So the top right, you see what bad things you are getting from the system, right? Yes, we talk about biomass. We say biomass is clean. Yes, biomass is benign. Biomass is clean. It doesn't give you carbon dioxide. But I should not say it doesn't give carbon dioxide. It gives carbon dioxide. But we consider biomass to be carbon neutral for the simple reason, because it traps carbon dioxide into itself in its upbringing process also. So that's why we call it clean. But the system is not really clean. There are many questions that needs to be addressed. Right? What to do? How do we discharge the tap? How do we discharge the effluent water? How do we assess their performance? We will hardly do that. These are the open questions that need to be addressed by researchers like you. But the system is okay, that works fine. This is just talking about the cleaning processes, what can you do, what kind of impurities are there in the gas, how can you remove them. These are primarily in the low temperature techniques. There are other techniques which operate at higher temperatures. I excluded them. At high temperatures, many of the things will get converted as well. So the treatment methods are not supposed to be same if you do it at low temperature or at high temperature. So that's another issue, not this matter of discussion. But primarily, as we have seen, the things that we have seen in meeting, those were basically these things. We had this scrubber, this water spray is basically the water scrubber, and then we had this cyclones. We had a cyclone there also for taking out the particles, the solids. The solids can be taken out in cyclones. Then we had separate bed filters of different bed materials. This is to suggest that the cleaning has to be suitable for the end application or end user application that you are conceiving of. If you are thinking about IC engine, or if you are thinking about gas engine, or if you are thinking about something more, because the same gas can also be fed to fuel cell. I won't open up fuel cell here. Fuel cell is another area of research, but in today's lecture I have excluded discussion on fuel cells. But this slide is informative just to indicate that if you are looking for using the same gas in fuel cell, you need to be more accurate in terms of cleaning of gas, because their tolerance levels are quite low. But okay, looking at all these things, we thought might be gas turbine is a good one or better one. Why? Yes, forget about fuel cells. Fuel cells at the moment is not going to be everybody's technology because of cost complications, or since it's still on the learning curve in a sense, or in the development stage, it cannot give you competitive systems. So we try to look at the options that we have for ready development. So we try to look for the systems, or try to look for system based on gas turbine. Gas turbine is a mature technology, and one good thing for gas turbine, its readiness to go for combined cycle. Gas turbine also is a cycle. Brayton cycle is there in the gas if you are looking for ER. So the ER standard cycle behind the gas turbine is Brayton cycle. Now Brayton cycle works at higher temperature, so therefore gas turbine can give you exhaust at high temperature. So if the gas turbine gives exhaust at high temperature, why not recover that heat to run another cycle? So gas turbine will give the way of combining another cycle at the bottom, right? So that way we can have a combined cycle still working on gasification. So that is what is called gasification combined cycle, or biomass gasification combined cycle. In the same parlance, we also have coal gasification combined cycle. These are also, we have plants. We have many plants all over the globe running on combined cycle, right? But gas-based gas turbine cycle are very common, right? Means not the solid fuel based, because say gasification based combined cycle means you are converting solid fuel into gas or liquid fuel into gas and then using in gas turbine. But the ordinary gas turbine cycle or combined cycle is basically the cycle where you use gas for gas turbine cycle and waste it for your Rankine cycle. And combined cycles, such combined cycles can regularly give you efficiency in excess of 50%. So that is the force, propelling force behind our thinking of in this line. So we try to go for gas turbine, but the gas turbine will not accept bad gas. So what we thought of going for indirect heat exchange. So we thought of a gas turbine cycle which will not directly be based on combustion, rather it will be based on heat exchange. So that way we could remove these things. So these are the benefits that you can draw for such indirectly heated cycle. So we went for such indirectly heated gas turbine cycle. Okay, the lower part has got cut off. So this is the system we tried to show that the gas turbine, after gas turbine, the exhaust is still recovered, the heat in the exhaust is still recovered in another cycle, which can give you work through Rankine cycle. So this is a very basic configuration of that combined cycle, but the gas is fired externally, so the gas is not combusted internally. Yes, its performance is fine, no problem, because it's a straightforward power generation system. We did not think about COP, we did not think about VCR, VAR, we did not think about even FESR because there is no cogeneration, simple system. So assessment was quite straightforward. We went ahead and calculated, and it was giving me very fine efficiency of more than 36% we are having, right? Considering a lot of losses here and there. Okay, other parameters we can ignore for the time being, so it is a good system. Now we thought, why not convert this system into a cogeneration system, right? So we will have so that top left is the gasifier, right? So the top left is the gasifier giving the gas. The top right is the gas turbine block where we are using the gas. Then the exhaust, and then again it is indirectly heated. So we are not combusting the gas into the gas turbine. So that's why we put that heat exchanger in between, right? One combustor heat exchanger. Together we call it combustor heat exchanger. You see the combustor and you see the heat exchanger. So you can consider this to be a combined unit which can be termed as combustor heat exchanger. In fact, we developed combustor heat exchanger practically. The few pictures are not here, but this also we have done. So this could be done, and then you could run a gas turbine. Okay, the gas turbine will give you power, and the waste heat coming out of that combustor heat exchanger can now be used to run a VAR system via a steam generation system, because the VAR needs generator, and the generator needs to be maintained at certain temperature. So the best thing is, steam is a very good heating element, because if you are using steam at saturation condition, corresponding to that equivalent pressure, you can maintain the temperature very nicely, right? The steam will get condensed and come back, but throughout maintaining the same temperature. So that is the beauty of steam. So we devised such a thing. We had a heat recovery steam generator, and that steam is going to the generator for the VAR system. So we have a cogeneration system, right, based on that theory that we discussed. And okay, maybe we could skip, but these are also required. But let me just touch upon it. This only shows the way that you can go for calculation of exergy, because exergy will be associated with every stream that is going into a component and coming out of component. Right? In theory, when you say, because in the first place you remember we are talking about exergy associated with the heat Q. But how this Q comes? It is carried by somebody, so that's why we call it stream exergy. When a stream enters, it will have its exergy because of its temperature pressure. We call it thermophysical exergy. Right? Because of its composition, it will have chemical exergy. Right? So basically, this slide is trying to show you the physical exergy expression. The next slide is trying to show you the chemical exergy of the fuel. This one is trying to show you the chemical exergy of a mixed gas. Right? So you can calculate chemical exergy and physical exergy, and you can add them up. So that's how you can because by exergy, this is one good thing about exergy. Every component you can study separately and you can find out, because in real processes there will always you will find the exergy is not going to be balanced. Whatever is going into a component, whatever is coming out of component, there will be some losses in reality. So your effort should be to minimize that loss. So this this study was primarily aimed at improving that part. So which component is the culprit, which is destroying much, we wanted to identify that. We will see the results. So sometimes we consider. I mean, this is one way of considering a component. The streams which are acting as causes, means cause effect. Something you are giving, something you are getting. What is your desired output? You consider it as product exercise, right? What you are giving, you call them at fuel exergy. So in a way, the exergy extraction will be the difference between the two. So one example is given for gasifier. For the gasifier, you have this, the biomass fuel. So fuel input, you have some air. So these two are input stream. The gas you are getting as output. So you take the difference, you will get the destructive part, right? And therefore, you can also get the efficiency on exergetic front for the same component. So that's how you can have the exergetic efficiency on the component basis, not really for the system, but yes, for system also you can do it. So this is the beauty of exergetic analysis. Well, so based on the funda that we derived, we devised these terms. Nothing new. Only thing, we proposed a new way of, instead of efficiency, here we put this exergy utilization factor. Because that is a cogeneration system which is producing work as well as coal. So we thought we considered, on exergetic front, how much we could utilize. So in a way, this is kind of exergetic efficiency in a weird sense, right? So we considered the work as well as the exergetic equivalent of the cooling effect, and these two we considered. So here that's what we try to do. Okay, and we also have seen for the steam generator considered aviation, but this is immaterial because the same steam we are using for the VE. Well, look at the data. Now, the overall efficiency is close to 22% after all these things, but we are getting good amount of cooling effect. Now, see, the plant was basically giving you 100 kilowatt of work. Right, 97. This particular configuration which is giving 900. So this 100 kilowatt system was giving me 185 kilowatt of cooling effect. Right. So it's good utilization wasted. I didn't do anything because the same plant that we discussed earlier, which was giving me similar configuration. So a little bit of this and that. So and this is good enough. Still giving me 22% water exergetic efficiency and giving me nearly value of 2. So good plan, not bad. We try to see the flow of exergy through all the components, how much exergy, right? So this is this you can say the climax of this study. This on a diagram shows which component is losing how much exergy. So directly it shows you the culprit. For example, the gasifier. For example, the VR unit itself. Right, for HRG also. So this 3-4 components are responsible for more than 50% of the losses. Not losses, exergy destruction. Right. So that is so therefore, if you want to improve, you should look at the gasifier. You should look up the VR unit. You should look up the combustor. You should not look at the gas turbine. This shows where you should look for improvement of your plant. Right. Okay, now that is about the technical thing. What about the price? Because I said this is another parameter we need to judge. So how do we judge? Now, price of electricity, cost of electricity is a very common term we have been using for years. But here we are not only using electricity, not only producing electricity, we are producing coal, producing this one. So how do you, because to produce that coal unit, I put some unit, gear unit, it has got its own cost. That cost component is also coming to the cost of the plant. So if I take cost of the plant and then only consider the electricity, I cannot hold my price. Obviously, my price will not be competitive. But I know I have done a good plant. So what is the right way of comparing its price with other competitive offers? So we thought, yes, if we have a cooling plant, If we needed this cooling plant separately, then we needed electricity. But here we don't need the electricity because we are getting the waste heat and we are utilizing the waste heat to run the cooling system. So why not? If you look at the second term in the denominator, right? This avoided electricity for cooling. What it means? That means because of this integration of the two plants, I avoided consumption of this electricity, which otherwise I had to consume to run my cooling plant. So this I have avoided. So therefore, I have every right to consider that extra electricity in the denominator as if I am producing that electricity, I am running the cooling plant. So this is what we proposed for such cogeneration system, right? Because that gives me a sort of level playing field when I try to compare my plant with other plants selling electricity. These are costs. These are, for example, yes, let me mention the three terms. The first one is the capital cost, but these are annualized, because all the capital costs are annualized. Means what is the component that you need to consider for this year? And yes, and the fuel cost. Yes. So now it's step forward. So three components. These are the three usual components of cost analysis. What we consider, the first one is basically coming from your investment. The second one is coming from the running your system. The third one is coming from fuel. Sometimes apart within operation maintenance, you put the wage related cost. Sometimes you put separately. We club it together into the same model because that is basically the head for the running of the system, right? So together the numerator shows all the costs involved in the one that will be on my head for the year, and the denominator gives me how much power I am going to produce that year, considering the additional one which I am not producing, but I am saving because of the cooling. Because my cooling plant is not requiring that electricity anymore. So I added this in the denominator. So now I find, so that we call effective price of electricity or effective cost of electricity. Right? So this way, now see what price of electricity, what cost of electricity you got. The cost of electricity is 0.05. This is good enough. To translate it to, it will be something around 6 or whatever. So per kilowatt hour, that is going to be the cost for this one. Okay. This also considers a payback period analysis because, as I mentioned, how long, because you are selling electricity in this fashion, right? And you are investing. So how long it will be taking to get your money back? Thereafter, it will start making money on its own. So that's what we call payback analysis. So we have the payback analysis somewhere else. What more can we do? We can think of two storage. So in the basic configuration, we didn't think of storing heat energy, neither did we think of storing electrical energy. So to improve its availability, now you can think of two storages. One is your thermal storage, the other one is your electrical storage, let's say in battery. So these two storages we incorporated. This is more like the physical configuration. The first one is basically the flow. This is basically more like the physical configuration. So with that, we still would get a value of this one. The value cost is higher because of the storage. The storage means we considered battery storage, lithium-ion battery. That was giving us quite heavy cost component, and also the thermal storage we considered some kind of storage, right? So but with that the payback period is now extended. Earlier we were getting it 5-6 years, now we are getting it 14 or 14 and a half. So you can always balance, but if you have this kind of plant, you can say your plant will be able to run throughout the day of life. Even without the power unit, the cooling unit can run for some time. The battery can supply you for some hours. So that enhances the availability of the system throughout the day. The earlier system may not give you, and that will also impact the design, or the install capacity of the system. If you are considering storage and not considering storage, that will also impact that. Yes, looking at the payback, you remember in that second slide you mentioned we should also look for what framework is in place on the policy front. Is my government supporting my endeavor in a way or the other? Are the banks giving me soft loans? Right? So, is there any policy support? Is there subsidy available? Because this subsidy term is what we know very much. So, the study was extended to consider variation in subsidy, and we tried to see the impact of subsidy. Right? So, in fact, a 50% subsidy is good enough to bring its payback period at par with the basic system, but the system is with storage. Right? So with costly storage, I am still able to match the payback period of the earlier one if government gives me subsidy. So on different subsidy, so that way you can vary the subsidy level and you can see its implication on your payback analysis. So I mean that is how we try to do this. What more? As I said, we always look for multiple opportunities. So that's what we did. Cogeneration is one way of combining two things. But there is another way of combining things. Why only look for one source gasification with biomass? Right? Why not look for other resources on the source side? So this is called source side hybridization. So you can make a hybrid system on the product side as well as on the source side. So this is one instance we consider. Let's see what is the effect of connecting one solar, because that means I will get free solar energy. I only need to make the system and then consider it. Right? So what is the effect? Let's see. So this is what we did, and not only that, this is a tri-generation. You see the third component? The third component lies here. So you see the third one, the domestic hot water. So basically it's a tri-generation. I am getting what? I am getting cooling. I am also getting heat in district water heating system. Right? So say another logical development of the other system. So how is it performing? So what parameters we should look for? Yes, the parameters are getting a little bit skewed because more terms are coming. For example, here you can see I think a chart should come, but it's not coming here. It's showing overall efficiency, considering three effects. It is also showing COP, right? It is also showing the collective efficiency of the solar front. It's also showing electrical efficiency of the gas turbine unit, and now it is these other values. So it's still it is giving you electrical efficiency. We had a shortfall because of this. Earlier, if you recall, we got it 21-22%. Now we got 19%. The interesting thing is, if you look at the efficiency phenomenon, I mean overall efficiency, because now overall efficiency means my input is not only biomass, my input is also solar. The efficiency is dropping in the midday. Why? Because I am utilizing a lot of solar, but solar is not good when you look at its utilization. So we are taking too much solar energy, but not able to convert it that way or store it that way. So its efficiency is falling. But never matter, because I am not buying solar energy. I only try to enhance the effectiveness of the system. Now see what is happening on the price front. Okay, here also we devise the price, but see on the price front, we also deducted from the cost in the numerator the heating. Why? Because we are getting heating, so that heat we can sell. Right? So if the heat we can sell out, so that can be adjusted for the cost of my electricity. So that's how we propose. So therefore, we also deducted something on the numerator. We added something. Logical. So what we got? So we still got, see, without considering cooling and heating effects, the price of electricity was going to be nearly $0.1 per unit. Now with consideration of this thing, the effective price is coming down to 0.07. Right? So that is the, Why are we talking about that? Because that is the way of, because otherwise I think you cannot justify your price. Somebody will say, okay, you have developed something, but it's at a high price. But actually it's not, because I have a tri-generation system from where you can sell your heat, you can also sell your cold storage plant. Right? So therefore we adjusted here and there, and we are effectively you are basically costing your energy, your electricity is costing this much. So this is how you need to sell your system. It's a tri-generation system. Okay, what more? Is that all? Other evolution also there. Look at the gasifier, the bottom of the gasifier. And we have shown you earlier, the gasifier is not a good one, it is giving me too much of torque. It will give you quite good amount of ash, and this biomass, particularly the rice hulls, they are rich in silica. That is also costly. Can you recover silica? Yes, you can attempt. If you can recover some material from the waste of this plant, you still have an edge, another edge you can add. So that way, by adding complexity, you can draw benefit on cost front, on environmental front, because the moment you recover something, you are treating the waste, you are trying to sell the converted waste, so that will be giving you effective product with lesser waste. Right? So these are the directions we should move. I mean, we need to define. Yes, on technical front it's done, because if you recover some material, you can still consider, because any material recovered means it will have its chemical exergy, like fuel. So you can add it up into your exergetic analysis as well. First, how to go about the fuel or cost front, how to go about into the environment fronts. So these are the open questions one must look at and one must think about. I hope with that I would come closer to the end. This is showing biochar is one such thing, product that you can get from gasification. Right? It has got its utility also. Biochar is a good fertilizer. You can sell it also. And as I said, if you could recover silica, that's another thing. You could sell. Recoverable products that you can add to your system, definitely add to the system, but that will also add benefits on cost front, on environment front, on all other fronts. Right? Yes, since this analysis was based on biomass, we didn't include analysis on environmental front. Otherwise, you could go for example, we had studies where if we could reduce carbon emission, we could find out how much saving we are going best compared to a reference plant. We could find out if we decrease carbon emission, what is the equivalent benefit in terms of cost for the savings on carbon emission. So these are the analysis that we can do, or we keep on doing. We do that on other systems. But for biomass also now we are doing, why? Because of this great advantage of biomass. Biomass by definition is carbon neutral, because even if we combust biomass, we don't say it's producing carbon dioxide, because the same carbon dioxide will be trapped by the biomass in its gestation process, in its bringing up process, in its plantation process. So by default we consider biomass as carbon neutral, although truly biomass systems cannot really consider carbon neutral because of other ancillary operations. You need to transport biomass, you need to process biomass. All this will be costing something, some processes where you will be incurring some carbon emission. So on life cycle basis, so this is only on the product basis, on the system basis. On life cycle basis, you should consider all the processes involved. So this study is not expanded to include the life cycles. But on the face value, we consider biomass to be carbon neutral. Now that gives us opportunity. For example, short while back I have shown this char, biochar. So if I recover biochar, if I recover some carbon from the system, that means you are basically reducing, recovering some carbon. That means you are trapping some carbon. That means you are not allowing some carbon to go out. Instead, you are capturing carbon in as carbon form, and might be you are putting it into the into your subsurface. So that way, carbon, this biomass-based systems have the potential of being carbon negative. And this is now the focus where we all are, pursuing, trying to develop. We have a few studies on carbon negative systems, but I am not sharing the results of those data now, because here I try to share primarily the thought-provoking expressions where the simple assessment parameters are going wrong, or if not wrong, why insufficient, because the parameters are not really wrong. They have been proven, they have been used for years, ages, for centuries, but they are proving insufficient when we try to consider complex systems. So how can we look at that? How can we bend these things in our favor? So that's all about this. With that, I will close. If I want to sum up, the things that come out from this is obviously, yes, the conventional single objective assessment like efficiency based on one product is insufficient. Yes, hybrid and multi-product systems are receiving increasing focus day by day. We all are going for is an effective for but other parameters need to be, and in fact that is why I didn't include them. That is why these days we have 3E analysis, 4E analysis, energy, exergy, economy, environment. Then these days we also say techno-economy, we also say exergio-economy, we also say exergio-environment. So these terms are coming on, right? These days we have 5E analysis, 6E analysis. But anyway, those are traditional. I just wanted to share where the traditional assessment techniques are falling short in our assessment of this multi-product systems. Okay. So with that, I close it here. Thank you very much. If you are looking, yes, most of the data that I have shown here are coming out of research work of doctoral scholars in our institute, in my department. So I am not taking names of any particular scholar. You could go to the institute website or department's page or my page to look at the publication list, which will include all the authors there, so you know who has worked where. So, and what are the different works that we are carrying forward at IIST. And I invite expression of interest of joint work through collaboration, through cooperation, through student exchange, whatever is possible. Thank you very much.
So the floor is now open for questions. If you have any questions, please first.
Sir, one question.
I'm sorry, it was a long dinner, but anyway, but time was allowed, I think, to 12 for me. Yes, please. Any queries? I may not satisfy you or satisfy you all, but I would attempt. Yes, please.
Sir, what will be the outlet gas composition after gasification of the biomass or biogas?
Wait.
And how we can calculate it?
How we can calculate? Wait, I will try to answer that. To your first query, what is the usual gas composition? When you gasify a solid fuel, let's say, the solid fuel means it's a hydrocarbon fuel. It is going to contain carbon, hydrogen. If it's biomass, it may contain a little bit of nitrogen. But anyway, we should say it's a CHO, carbon, hydrogen, oxygen will be there in the fuel, be it coal, be it biomass, or be it any other liquid or gaseous fuel. So when you gasify that, gasify is basically halfway of combustion. It's a partial oxidation. Means if you are combusting, let's say you have carbon, only carbon, fixed carbon. If you combust it totally, it will give you carbon dioxide. So if you are producing carbon dioxide, that cannot really be used as fuel anymore, because it has reached its saturation stage in that fashion. If I am allowed to use the term saturation, it's not a right word. But if you go halfway, means if you provide the system with insufficient oxygen or insufficient oxidant or insufficient air, what we will produce instead of carbon dioxide, we will produce CO. Now CO is the fuel, CO2 is not. So my attempt will be to convert the solid fuel or liquid fuel into such gaseous fuels which are burnable, which can give me energy when combusted. So therefore gasification, even the most common gasification is air gasification, because air is readily available and within air we have oxygen. So basically I have to go for oxidation halfway, partial oxidation we say, right? So we say equivalence ratio. Equivalence ratio, what means you are giving stoichiometric oxidant. If you give half stoichiometric oxygen, it cannot combust fully, so it will be partially oxidized. So that gives us the liberty of getting the middle products. So if you are starting with carbon, you will get CO. If you are starting with hydrocarbon, you might get CO, you might get CH4, you might get higher hydrocarbons. Means CH4 is the single C species. You can get C2 species, you can get C3 species, you can get, these stars are also hydrocarbons. The only thing these stars are primarily, say aromatic compounds. Benzene, toluenes, naphthalenes, they are, or other derivatives. So tar is basically a mixture of all such bigger hydrocarbons. But they are all hydrocarbons. If you are able to convert tars, you will get energy, heat energy out of that. So all these are, when they are in gas form, they are in producer gas. The tars are in liquid form, you segregate. The chars are in solid form, you segregate. So that do not go into gas, but some of the tar are in vapor form. So they are also carried over with the gas. So in essence, to summarize, the gas will have methane, the gas will have CO, the gas will have moisture, CH2. The gas will also have N2 because you have gone for air gasification and the nitrogen mostly remains inert. So the product gas will have these components. Although there will also be CO2, there will also be a little bit of let's say other hydrocarbons which remain in gaseous form, but primarily CO, CH4, H2O, these are the primary components. Yes, please.
Sir, is it possible to use alright form of biomass pellets?
Yes.
Mixing with the coal and spraying into the boiler directly?
Yes, in fact, these days, many of the utilities are mandated to use or try out a little bit of biomass. For example, NTPC has started co-firing, we call it co-firing biomass pellets with, because if you are trying to see, two ways are there. Either you can go for separate utilization of biomass and coal, or you can think of utilizing them in the common application. In pulverizer, to pulverize coal. So you might say, how can we give biomass into pulverizer? You cannot give raw wood or raw leaves into pulverizer. So you need to process that. So process means you can make pellets or you can make briquettes. So pellets is the one which are the smaller ones, which are more condensed, which you can use with. It's more conducive to pulverization. Briquette is more conducive to, for example, in gasifier. In our gasifier, we could use briquette.
But another question is the initial temperature of the biomass
that creates problem, but that is why you cannot go on mixing biomass as open, right? So people are trying 5%, 10%, 15% biomass, but those are also giving enough problems, but not really because of their flame characteristics, but because of the byproducts in a way, I should say. The biomass is giving too much of these things which are getting sticky. Depends if you are able to maintain good level of temperature and the reagents, your furnace or the reactors. If I say boiler, that will be operating very fine. But increasing the ratio has got limitations unless you develop the technology or you have a very good palette. But palette is meant for that. In palette, we reduce moisture. It has grindability like coal. So just like coal, you can grind a pellet also. So that's why pellet is a better one to mix with coal than briquettes. Yes.
Sir, in the cold storage space, cold storage space,
Cold storage.
instead of using VCR, you are using VAR. Why? Because we know the COP of the VAR is very less than that of the VCR.
Yes. Somebody was also from the backbench. Any more queries?
I would like to know a little bit more about the decades.
Okay, that's separate. So let me address this one first. This query is why are you going for VAR? I think I explained that also. You had two options. The topping gas turbine system was producing work. So you had options of splitting the work and using it. But since I do not want to, encroach upon the workflow, because the primary objective was to produce work. So after producing work, why should I use the same work for my cooling system? So we thought, let the work go as it is. But the plant is still giving me waste heat. So let us look for utilizing the waste heat. So that was the driving force when we thought of going for VAR's coupling with the generator. Yes, and here to respond to your query, briquette is is basically a process. Fuel processing means, as I said, you cannot really use let's say leaves or woods directly into the reactors. That will not go well with the grate. If it's a grate type boiler, your reactors might be of different types. Right? Such fuels might go well with fluidized bed systems. You might have heard fluidized bed system. Fluidized bed system is a good thing which virtually eats up anything, whatever you do, small or bigger. But for other units, you need to give these things in a processed manner. So briquetting is one form of processing the fuel in a safe and still providing porosity and means it's giving you some unit, it's a size which is burning, because eventually you test how it's burning, how it is responding in a burning experiment. So that's how briquettes are done, and on briquettes also you can alter the moisture. Right? So everybody would like to go for drier briquettes, but as I said, briquettes have also got its limitations. Using briquettes in pulverizer may not work out well. If you give too much of briquettes, the pulverizer will jam out. So that's why I said, these are different ways of treating the biomass to form either pellet or briquette to suit your aim consumption mechanism. Yes, please.
Can that briquette really replace coal-based products? Because in recently Hindustan Unilever Nadia unit, they are being shifting towards briquette instead of coal.
Yes, it can. Means theoretically it can. Logically also it can. Practically it's becoming difficult. For example, in the first place, matching the heat value. We didn't talk about the comparative heat value. 1 kg of coal will give you, let's say, 26 megajoule. 1 kg of biomass will give you, let's say, 5, 10, 12. So the heat value is not at par. So that's why burning the two simultaneously has got, responding to that question this way also has got limitations. These are of very unequal heat value situation. Right? So therefore you cannot, and therefore you need think of the quantum. So you had a system just designed for coal. Now you want to run it for briquette, biomass briquette. So how much briquette would you put into the reactor? It has got its limitation. So naturally you would not be able to generate the heat that was designed for the reactor when it was based on coal. So pulverized coal, if you are designing something for pulverized coal, if you want to replace it with briquette, it will be giving you let's say 40% or 50% rated out anyway. And that again, the all your burning systems means burners, its ducts, they need to be changed. Right? So these are issues, but theoretically, yes, that's how people are changing. Now, in Europe, people are moving from coal-based plant to biomass-based plants. In other here I didn't include pictures of there are biomass-based the similar plants, the combined cycle plants are there, but not the one that we consider. We consider the one without firing, indirect firing. The indirect based firing is not readily found in commercial operation. But biomass plants, biomass boilers are very common. Biomass boilers are very common, not for power generation but for utility heat generation. It's quite common. In our country also, there are plants who use, for example, in pulp and pulp paper, they have the byproducts, waste products, they use it. I was associated in a project where we were using this pulp, ITC. Right? So biomass is possible, but then you have to think of its, how do you source? To run a 100 megawatt plant, how much biomass you need? Go for calculation. It will be, let's say, 3 times the coal requirement. Then you have to draw that biomass on continuous basis. So how we are not really matured enough to go for biomass cultivation, right? So, for example, when the focus was on biodiesel, there were commercial plantation for jet rotor dedicated. For biomass plants, we do not really, but that's why biomass plants you will find in as distributed systems. There are many distributed systems in India. I happen to visit a lot of such plants, small plants. 100 kilowatt, 200 kilowatt, 300 kilowatt. If you go to, let's say, people residing near Bardwan, they have rice mills. This rice mills produces this rice huts. So many of them have installed their in-house generation system. I happen to visit the system. Small one, very big unit. The entire consumption of the plants are being made by biomass generation. Yes, they have issues. For example, the star issue, the bad water discharge, the wastewater discharge is issue, the smell, bad smell. So issues are there, but they are not depending on the grid electricity. They are generating their own power. So the plant generation is fine. The plant economy is also fine because they are producing the rice hucks. They are also getting rice hucks from other plants nearby at cheap price. So a lot of matters, lot of factors are involved in sustenance of a plant. Yes, any more queries? Well, if not, I must thank you for your patient hearing and understanding of the system. Thank you very much. Thank you.
Thank you, sir, for this informative deliberation. Now, I like to request our HOD and coordinator of the program, Professor Gautam Kumar Gur, to hand over to coordinator to Dr. Gur.
Thank you very much. So, thank Professor Dr. Sudip Ghosh sir. So he has been associated with me for quite some time, and apart from being an expert to our FDP, he is also a Board of Studies member of the Department of Mechanical. Okay, so we thank him for his valuable time. He has given his consent in delivering a lecture on a very emerging topic of power plant. So he is a very eminent professor in Bengal Engineering College. Then now it is IIST Singapore. So I hope that this session was very energetic, and with all his experience he has tried to deliver lectures on all the facets of the power plant engineering, the new technologies that have come in the field of power plant engineering. So a lot of inputs have been given to the faculty members as well as some of the students are also participants of this program. So thank you all. The next session will be starting from 2:30. Now we will be having a lunch break. So I will request all the participants to be assembled before 2:30. Okay. The next speaker has already arrived. He is Professor Dr. Subhashish Bhumil from IIST Singapore. He is an expert in 3D printing, robotics, okay, nanotechnology. So he has already arrived. Just after the lunch, please do come. We'll start the session soon because the speakers will be leaving back to Calcutta. So we don't want to make any delay. So just have your lunch and please do come in time. Thank you.
Just a small announcement. We have one more thing that we like to take photograph of with our experts.
So all the faculties are